wanted to go over a quiz, and it turns out I wasn't able to give you this quiz because of the way question banks are set up in Canvas. So I thought what I'd do is just give you the answers and walk through the reasoning behind them. I think this also makes a good point that sometimes the answers to a quiz depends on what's in the mind of the instructor. And I have one problem that I missed when I took the quiz. And I think it's just because, I didn't, well, first of all, I didn't watch all the videos in great detail. But I wanted to discuss that sometimes the quizzes, the instructor has certain things in mind. And maybe you could explain to me what you saw in the video that would give the answer that I missed on the quiz. All right, so let's go through it. The first question was, a delta t means an impulse function of height a. Okay, so when you first read that, if you're new to impulse functions, you say, oh, there's an amplitude a, so yeah, it's scaling this impulse function by a. Well, the problem is an impulse function is infinitely high, all right, and so Professor Miller knew that, and so you're supposed to take into account that scaling a value of infinity is still infinity, all right, so the area underneath the curve of a delta t, all right, if you integrated a delta t, you would get a, all right, because I call it the weight of the impulse function is a. All right, so that's why that answer is false. Okay, question 2. The signals we are interested in are physical quantities that vary with time. And I assume what he meant here by physical quantities, voltage, displacement, things like that, things that you can actually quantify in some sense. So I chose true on that, but I have to admit, I wasn't really sure if he meant, if he was trying to tease out some subtle difference here between physical quantities and abstract signals. I think you could also have an abstract signal that's not necessarily associated with a physical quantity. And so, that's why I was a little queasy about my answer on that one. All right, and that speaks to the point of what I'm trying to get across with this video when I'm explaining this quiz. Okay, a discrete signal has a small amplitude, making it difficult to measure and often requiring amplification. Well, it's true that there are a lot of signals that are small in amplitude and difficult to measure and require amplification or filtering, but not necessarily because it's discrete. The discrete part is what makes this false. And, it's also implying that all discrete signals fall in this category. And that's simply not true. Some signals are not hard. Some signals are sampled from, it's usually sampled from analog signals that are, large enough in magnitude and easy to measure and don't require amplification. All right, so that's why that one's false. Okay, if a signal is causal, that means we can express it mathematically. I think he means, when he says express it mathematically, I think he means a closed form expression. And there are lots of signals that we can't express mathematically, and it doesn't depend on whether it's causal or not. All right, so in general, there's signals, some can be causal, some can be not, that we can't express as, like, for example, a transcendental function or something like that. Okay, so that's why I chose false on that one, and I agreed with his response. All right, here's the one I missed. According to the quiz, it says, for our purposes, a system is defined as a set of components that perform a specific function. Okay, so maybe there's something in the videos that I missed on that. I chose true because that does seem like what we're using a system for. A system does something. But I guess, maybe he's teasing out that you can have a system that doesn't perform a function. It's just a consequence of the system, all right? Some physical model that you're looking at. And there's no specific function you're trying to get out of that model. It's just reality, what you have to live with. So that's my guess on what he meant by choosing false on this one. Okay, if a system is causal, that means its response only depends on present or past values of the input. And yes, that is the definition of causal. Time invariant means the system or equation parameters do not vary with time. Okay, so I think what he's talking about here, this is what I kind of gathered, was that you can describe a system with, for example, a differential equation, and if it has constant coefficients, those coefficients don't vary with time. Those constant coefficients would be parameters. Okay, and so if you have a differential equation where the coefficients vary with time, it is not going to be time invariant. So that was what I was kind of thinking he was meaning, and so I chose true, and I think I, jived with his interpretation. Okay, question 8. A linear system always has an offset like an intercept of a line, y equals mx plus b. Okay, so this is a common thing about linear systems. It turns out a linear system will never have an offset. Okay, so for example, if you put a 0 in, if I put x equals 0 into this equation of a line, you get out the constant b. Okay, all linear systems have the property that if you put 0 in, you get 0 out. Okay, so the point he's trying to make also is the equation of a line. That's a line. That's not that's a mathematical equation of a line. That's not a system definition. If you were talking about a system definition, you'd be putting in a signal x of t, not just a single point. It would be a whole signal, and the signal y of t equals m x of t. That if you define a system that way, this is not a linear system. Okay, so I knew the answer on that one was false. I was really confident about that because I know that definition of linear systems. Okay, convolution always allows us to find the response of a linear time invariant system. LTI is important. If he said a system, that this wouldn't be true. It has to be linear time invariant so that you can give an arbitrary input, you can find the system's impulse response. Okay, so arbitrary has some limits on it. You can define some really weird functions mathematically that wouldn't work, but from an engineering point of view, all practical inputs can be expressed using convolution. Okay, and finally, question 10. Convolution can be thought of as the sum of responses to an infinite series of discrete impulses whose heights are scaled by the input of the function. And yes, that's in fact true. So if you look at the derivation of the convolution integral for describing a linear time invariant system, that's exactly the step you take. All right. So it's nice to be able to describe that in words. So I'm hoping that fits with what you think of when you think of convolution. Okay, so that's walking you through the quiz. Hopefully that you find that helpful. I wasn't able to import the question bank because of system privileges settings. So let's use this instead of the quiz. All right, hopefully that was helpful.